Okay, today we're going to take a look at probabilities as they pertain to overlapping events or mutually exclusive events. When we look at problems that are mutually exclusive or overlapping, there's one gigantic keyword that comes into play, and that keyword is or. Now, earlier in the week we did some problems where we were looking at probabilities, or late a couple sections ago, where we were looking for probabilities of two things both happening. This is now a situation where it's one or the other, and that changes our probability a little bit. When we have two outcomes with events in common, they're called overlapping events. When two events don't have any outcomes in common, they're called disjointed events. Now, when we take a look at these problems, the key word here is you're going to see an or in that, and that means we're going to add our probabilities. Now, when events overlap, because it is possible at times for certain things to have both things happen in the problem, and then we're going to go ahead and subtract the probability of both things occurring at the same time. Okay, we're going to add our probabilities and then subtract the probability of both events occurring at the same time. When your events are disjointed, okay, which can also be referred to as mutually exclusive, you don't have to subtract because both events occurring at the same time cannot happen. Okay, for example, as we go through with these problems, you're going to see this come into play a little bit. We're going to be spending a lot of time taking a look at cards and pulling cards out of certain situations. For example, a card is randomly selected from a standard deck of 52 playing cards. What is the probability that the card is a 10 or a face card? All right, so what we're going to look at is the probability of pulling out a 10 first. Okay, how many 10s are there in a deck of cards? Okay, 4 out of 52. Now, when we worked with the problems where we were multiplying our probabilities with our and statements, we wanted to simplify and reduce down. Because you're adding and subtracting the fractions, we don't want to do any reductions or simplification of fractions until the very, very end, because we're going to have common denominators through most of our problems. Now, how many face cards do we have in a deck of cards? Well, there are 4 suits in a deck of cards and 3 face cards in each suit. So that means that we have 12 total face cards out of the 52. Is it possible for a card to be a 10 and a face card at the same time? Okay, it is not. So as a result, those are mutually exclusive events. So what we're going to do is we're going to simply take 4 plus 12, and we're going to add those together. And that gives me 16 out of 52. Now, when I take 16 out of 52 and I simplify it using the fraction key in my calculator, it does reduce down to a 4 out of 13 chance that you get a 10 or a face card. Again, those are mutually exclusive events because you can't have a 10 and a face card at the same time. There's no overlap. Okay, here's another example. Okay, we want to take a card that's randomly selected from the standard deck of 52 playing cards. What is the probability that the card is a spade or a face card? All right, so how many spades do we have? Okay, there are 13 because there's 13 cards in a suit. Okay, we said that there were 12 face cards in our deck total. Okay, so that's going to be plus 12 out of 52. And then the catch here is, can you have a face card that is also a spade? Well, that answer is actually yes. Okay, because you've got a jack of spades, a queen of spades, and a king of spades. Okay, so that means that there are 3 face cards that are spades. So we need to subtract those off. So minus 3 out of 52. 13 plus 12 is 25, minus 3 is a 22 out of 52 chance that you will pull a spade or a face card. Again, we're going to use the fraction key on our calculator. So we take 22 and divide it by 52 to find our decimal, and that will simplify to 11 out of 26. Again, either answer is going to be fine. Okay, but the key thing was that you had a face card that was also a spade. So those events overlapped. Okay, a card is randomly selected from a standard deck of 52 playing cards. What is the probability that the card is an 8 or an ace? Okay, how many 8s do we have? Okay, 4. How many aces? 4. Can you get an 8 and an ace at the same time? No. Okay, so we add those together. So we got an 8 out of 52 chance of those things happening. And 8 out of 52, those are both divisible by 4, simplifies down to 2 out of 13. Okay, so when you're looking at the overlapping events, The key thing is, can they both happen at the same time? If they cannot, then you're good to go. A card is randomly selected from a standard deck of 52 playing cards. What is the probability that the card is a 10 or a diamond? Okay, well, how many 10s do we have? Okay, there's 4 10s in our deck of playing cards out of 52 cards. How many diamonds? Okay, 13. How many 10 of diamonds are there? Okay, there's 1. So we're going to subtract 1 out of 52 off because that's our overlap. 4 plus 13 is 17. Minus 1 is 16 out of 52. Again, both of those are divisible by 4. Cuts us down to 4 out of 13. Questions on that? So you're always looking for the overlap. Okay, if it's an or statement, you're going to add the probabilities together, look for the overlap, see if there is one. Okay, if there's not, you don't have to subtract. If there is, you do. Okay, out of 200 seniors in a senior class, 113 students are either varsity athletes or on the honor roll. There are 74 seniors who are varsity athletes and 51 seniors who are on the honor roll. What is the probability that a randomly selected senior is both a varsity athlete and on the honor roll? Okay, now, this one actually is kind of a complementary event type deal. Okay, because we're going to look for students who are on one of these and then subtract the total number of students who are on. Okay, so if we look at our varsity athletes, how many seniors are varsity athletes in this class? Okay, there's 74, and there's 200 total in the class. How many are on the honor roll? Okay, 51. Okay, so those are my number of students who are athletes or on the honor roll. And we know that there's a total of 113 that are in both, so we're going to subtract that 113 off. Okay, so this is a complementary event type problem. If I take 74 plus 51, I get 125. And I subtract that 113, and that tells me that I have 7 or 12 who are students who are both a varsity athlete and on the honor roll. And if I take that 12 over 200 and simplify that down in fraction format, that comes out to 3 out of 50. For every 50 seniors, there are 3 of them who are both varsity athletes and on the honor roll. Now, we're also going to take a look at how this applies into probabilities when you're looking at percentages of different things happening. The American Diabetes Association estimates that 8.3% of the people in the United States have diabetes. Suppose that a medical lab has developed a simple diagnostic test for diabetes. It's 98% accurate for people who have the disease and 95% accurate for people who don't. What is the probability that a medical lab gives a test to a randomly selected person and a probability that the diagnosis is incorrect? All right, what we're going to do is we're going to find the probability of a correct diagnosis. And then we're going to use the complementary event or complementary probability idea to find out the probability that it's incorrect. Now, there are 8.3% of people who are diagnosed with diabetes. That test is 98% accurate. So I'm going to multiply those two together. At the same time, it's 95% accurate for those who don't have the disease. All right, well, if there's 8.3% of the population that is, that means that there's 91.7% of the population that doesn't have it. Now, what we're going to find is the accuracy rate on a positive basis. So I'm going to take 0.083 and multiply it by 0.98. That gives me 0.08134. At the same time, then, I'm going to take the 0.95 and multiply it by 0.917. And that is going to give me 0.87115. I'm going to add those two numbers together. Okay, and that comes out to be 0.95249. Now, that is our probability of a correct diagnosis, okay, which is about 95.25%. What the question asks, though, what is the incorrect diagnosis rate? Okay, so what we're going to do is we're going to take that 100% total we have, subtract 95.25%, and we'll find out that it is 4.75% inaccurate. Okay. Are there any questions on that? So we found our percentage of people who got the accurate test, and then subtracted from 100 to find the inaccurate rate. All right, so the next problem deals with a basketball team, and it is slightly different from that. When a high school basketball team leads at 60% of the games in a season, okay? So in 60% of the games, which is 0.6, they're ahead, which means in 40% of the games, they're behind. If they win 80% of the time when they have a halftime lead, we're going to take 0.6 times 0.8. And they win 10% when they don't, so we're going to take 0.4 times 0.1. And then we're going to find our probability that a team wins a particular game during the course of the season. When we take 0.6 times 0.8, that gives us 0.48. We take 0.4 times 0.1, that gives us 0.04. And if we add those together, that gives us a 0.52. That means that our team wins 52% of their games during the course of the season. Are there any questions on that? Okay, at this point, we'll go ahead and pass out the homework, and we've got the rest of the period then that you can work on that.